Hello students. Topic 20 is on properties of Laplace transforms. This is the second topic out of a series of 4 topics that focus on using the Laplace transform to solve ODEs with initial conditions. So fill in as much of the table below as you can, then return later to fill in the rest. Now we're going to be able to fill in these entries of the table. We haven't yet thought about what the Laplace transform of a constant function is. We can do that here rather quickly, and then we're going to use our last lecture on topic 19 where we did these 4, and so we're going to refer back to that topic, to our notes from that topic, to fill in this part of the table. The rest of the tables here we'll be able to fill in following today's topic. So now let's talk about if your function is a constant. To do the Laplace transform of a constant, let's do that work down here. You need to integrate that function, which is just a constant, times e to the negative st dt over the improper interval from 0 to infinity. Now the antiderivative of this is straightforward. Just divide by negative s. So we have k over negative s, e to the negative st, evaluated from 0 to infinity. Now if s is positive, the negative st would be negative as t goes to infinity. It approaches negative infinity if s is positive, which means this part here will shrink to 0 when we try to plug in infinity. So we get 0 out of this, and we only get 0 out of it, though, assuming that s was positive. And now we subtract, and now we plug in 0 and evaluate this antiderivative at t equals 0. So plugging in t equals 0 to this expression here becomes just 1, so we get negative k over s. And so we get a final result that's just k over s. And this is going to be our Laplace transform of any constant, k over s. Now for that to be true, s had to be positive. Now for t to the n, let's look back to our notes from topic 19. And on page 2 of those notes, we generalized the Laplace transform of a function that is of the form t raised to the n. And we got the result n factorial over s to the n plus 1. Now again, we have to assume that s is positive in order for the portion of the evaluation to shrink to 0. For example, right here, when we plugged in infinity into this exponential and got 0 right here, that was only true if we made the assumption that s was positive. If s is positive, then as t goes to infinity, e to the negative infinity will shrink to 0. So that's something we just want to make clear. So our Laplace transform of t to the n will be n factorial over s to the n plus 1. So we'll have n factorial over s to the n plus 1. And again, s had to be positive for that to be true. Now going back to our notes, sine bt. Let's find what page we did the sine. That was done on page 4. And the Laplace transform of sine bt was b over s squared plus b squared. And again, we had to have s be positive so that when I evaluated at infinity, we had these terms actually zero out in getting an answer. So b over s squared plus b squared. b over s squared plus b squared, and s had to be positive. Cosine bt. Back to the notes from last topic. Cosine was done right here, and the Laplace transform of cosine bt was s over s squared plus b squared. So we have s over s squared plus b squared. And again, s had to be positive for this one. And back to our notes to find the page where we did e to the at. There it is. It was on page 3. And we found that the Laplace transform of e to the at was 1 over s minus a, but s had to be larger than a for this to be the case. So 1 over s minus a, s had to be larger than a. Okay, so based off our last topic and the little bit of work we did down here, this is as much of these tables that we can fill in right now, but we'll come back and fill in the rest as we develop some more ideas. Okay, next slide. Use the identity below to find the Laplace transform of the functions that follow. So this is referring to this identity here is establishing the linearity of Laplace transforms, that you can effectively distribute a Laplace transform across a sum or difference of functions, and that constants can be factored out. So if you have a new function that's a linear combination of two other functions, f and g, so a times f plus b times g, and you want to do the Laplace transform of that, you really just have to do the Laplace transform of the f function and the g function separately, and then combine them in the same linear fashion. Okay, so if I want to find the Laplace transform of 2 plus t. Now, we actually did this last lecture by using the definition of Laplace transforms, but now we're going to do it by using this linearity approach and also using the table, the formulas. So capital F of s can be found by doing the Laplace transform of the 2 and then add that to the Laplace transform of the t. Well, the Laplace transform of a constant is just that constant divided by s. So we'll do that part first. So we get just a nice clean 2 over s is the Laplace transform of the first part. And then plus, and now we have to do the Laplace transform of t. So we're going to use this second entry right here where n is 1. Because t is the same thing as t to the 1. So we're going to get a 1 factorial over an s to the 1 plus 1. So a 1 factorial, which is 1, over s squared. So we get 1 over s squared. And this is the Laplace transform of 2 plus t. Now let's just compare that to what we did in our notes last time. The very first slide, we used the definition of Laplace transform. So we did this improper integral, and we got the same result, 2 over s plus 1 over s squared. Okay, now let's apply the property of linearity to this next one, g of t. So capital G of s, the Laplace transform of g of t, will be found by doing 2 times the Laplace transform of e to the negative 3t, and then minus, and then the Laplace transform of cosine 4t. And we'll be able to use the table above to do both of these. So let's go back up to the Laplace transform of e to the at. And this is true for any value a. A could be any real number. It's 1 over s minus a. So in this case here, a is negative 3. So we do 1 over s minus negative 3. That gives me s plus 3. And there's the Laplace transform of e to the negative 3t. And then minus, now let's do the Laplace transform of cosine 4t. So cosine 4t Laplace transform is going to be s over s squared plus b squared, where b is 4 in this case. So s over s squared plus 16. So s over s squared plus 16. And here is our Laplace transform. Maybe we could put that 2 in the numerator and write it this way. If you wanted to get a common denominator and push these together, you could. But let's not spend time doing that right now in this video lecture. Let's move on to the next slide. Now use the identity below to find the Laplace transform of the functions that follow. So now we're being given a formula for what happens if you have some sort of function being multiplied by a polynomial term, a power function of t to the n times a function. Now, I'm not going to prove this formula or spend time discussing why this formula works. I just want to demonstrate how it works and how to apply it. First thing we wanted to identify, so we're trying to find the Laplace transform of t cubed times e to the negative 4t. Well, if I can find the Laplace transform of e to the negative 4t, that's the role of the f of t in this case. Find the Laplace transform of this part only, and then do so many derivatives of it. Now keep in mind that this n that you see up here in parentheses, when you put the n in parentheses like that, it's indicative of a derivative, a number of derivatives. When you have the n as an exponent without parentheses, it's treated like an exponent. So this means negative 1 raised to the n, and then the nth derivative of capital F, as a function of s. All right, so let's identify that this is our f of t, the e to the negative 4t, and therefore capital F of s, the Laplace transform of that, is going to be 1 over s minus a, and a is negative 4. So 1 over s plus 4. So that's our capital F of s. Now I want to do how many derivatives of this? Well, that's indicated by n. So if this is t cubed, then I do, if n is 3, t cubed, then I do the third derivative. So we have to do 3 derivatives of this function, which means it might be better to write this as s plus 4 to the negative 1, so I can just do the repeated power rules. Okay, so next let's do repeated power rules on this. The first derivative is going to be negative times s plus 4 to the negative 2, and the chain rule would output times a 1, right? So I'm not going to bother writing that, but don't forget to do the derivative of the base when you're doing the chain rule. Second derivative, negative 2 times negative 1 is 2, and then times s plus 4, new power negative 3, chain rule is times a 1, and then we need to get up to the third derivative. One more derivative is negative 6 times s plus 4 to the negative 4, and then times 1 using the chain rule. And that's going to be this component of our formula. Okay, so capital G of s, the Laplace transform of the original problem, which is this t cubed times e to the negative 4t. According to this identity, we need to do negative 1 raised to the n, where n is the power that's on the t. So we're going to do negative 1 raised to the third, and then times the third derivative of the Laplace transform of f, where f is just this part, this factor of our g function. So putting these pieces together, we get negative 1 cubed is negative. Also, the third derivative is right here, so we're going to do negative 1 times negative 6. So we're going to get just 6 in the numerator, and then I'm going to move that s plus 4 raised to the 4 down to the denominator. And here is our Laplace transform. Okay, let's do the next one. Identify what the f function is here. That's this part right here is our f of t. So our capital F of s function, the Laplace transform of cosine 2t, refer back to our table. It's s over s squared plus b squared. So it's going to be s over s squared plus b squared, where b is 2. So plus 2 squared, which is 4. Okay, now how many derivatives am I going to need to find of this? Well, you look to the power that's on the t in front. It's t to the 1. So I only need to do one derivative here, and we're going to have to use the quotient rule to do that. So let's go capital F prime of s. We do the derivative of the top, which is 1, times the bottom, so s squared plus 4, minus the top times the derivative of the bottom, all over the bottom squared. And then we can simplify this. So f prime of s, we're going to have s squared minus 2s squared, so that's going to be minus s squared. So I'm going to put 4 minus s squared in the top, all over s squared plus 4 quantity squared. And we'll stop simplifying right there. We could certainly factor this top and say 2 minus s times 2 plus s, but I don't see any need. Nothing's going to cancel. So we'll stop that there. Now we go back to doing the Laplace transform of the little h function. So capital H of s will be equal to negative 1 raised to the n, where the n is the power that's on the t. So this t has a 1 power. So we just got to put a 1 power on this negative 1. And then times f prime of s. And now negative 1 to the 1 is negative. And f prime of s is sitting right here, so I'm going to have to multiply that numerator by negative. That's just going to swap the subtraction. So we can say s squared minus 4 instead of 4 minus s squared, and then all over s squared plus 4 quantity squared. Okay, now we can fill in a few more entries to our table. For example, right here, we can fill in this entry. So the Laplace transform of t to the n times f of t is going to be negative 1 raised to the n, and then we're going to have to do the nth derivative of the Laplace transform of f. So put this n in parentheses to indicate a derivative, and this is the formula we use for t to the n times a function. Okay, next, let's go to the next slide. Use the identity below to find the Laplace transform of the functions that follow. Okay, so here's another identity that I'm not going to prove for us. We're just going to learn how to use it. And this is where you have a function f of t times an exponential. And if you can figure out the Laplace transform of this function f of t, which is capital F, then you simply have to evaluate it at s minus a. And that's how you get the Laplace transform of this product, e to the at times f of t. Okay, so in the first example here, we have sine of 5t is our f of t. So let's figure out what the capital F of s function is. So sine 5t, go back to our table. Sine of bt is b over s squared plus b squared. So sine of 5t will be 5 over s squared plus 5 squared. And I apologize for the 5's and the s's, but this is going to be 5 over s squared plus 5 squared, which is 25. It's very easy to confuse s's and 5's, so be careful. And therefore, according to this identity right here, if we were to want to find the Laplace transform of g, so g of s, we would simply, and g of s, or g of t, little g of t is an exponential e to the 3t times another function f. And according to this identity, we just had to do the Laplace transform of f, find out what that is, capital F is, but then evaluate it at s minus a, where a is the coefficient of the at. So we just need to do the f Laplace transform evaluated at s minus a, where a is a 3. So in other words, this is simply going to give us 5 over, and then change s to s minus 3. So s minus 3 squared plus 25. And that is our Laplace transform of the g function. Okay, now let's go over to the next example. H of t equals e to the negative t times cosine t. So once again, I'm going to focus on this cosine of t. That's the f of t. And we want to figure out its Laplace transform, f of s. And the Laplace transform of cosine t, that's going to be s over s squared plus 1 squared. S over s squared plus 1 squared, so just s squared plus 1. So there's s's in a couple places in this one. And now referring back to our h, capital H of s, according to this identity, will be our f function, but evaluated at s minus a, where in this case, a is the coefficient of the t, so it's going to be s minus negative 1, so s plus 1. Okay, and this gives us, and there's a couple s's here in our f function, and we have to evaluate this function at s plus 1, so both s's get turned into s plus 1's. So s plus 1 over s plus 1 squared, and then plus 1. Okay, going back to our table, let's see, we can also fill in this one here. I skipped that one there. So if we're doing the linearity property, a times f of t plus b times g of t, the Laplace transform is going to be a times capital F of s plus b times capital G of s. And we also just now finished this one here. If we do e to the at times a function f of t, then we simply need to do the capital F Laplace transform, but evaluated at s minus a. Now this one here can be used to actually help us fill in these next three, because we have e to the at times sine bt. So if I wanted to do the Laplace transform of e to the at times sine bt, I just have to do the Laplace transform for sine bt, which is up here in our table, but evaluate it at s minus a. So in other words, we're going to get the b up top, and then divided by s minus a squared plus b squared. And then for this next one, for e to the at times cosine bt, I just have to do the Laplace transform of cosine bt, which is sitting right here, but evaluate it at s minus a. So this one has s's in two places, so we'll change both those s's to s minus a's. So we get s minus a over s minus a squared plus b squared. And both of these wind up being true if s is more than a. Similar to the domain for just the exponential alone. And this one, bottom one down here, can also be generalized by saying, okay, let's do the e to the at times f of t. So let's consider the t to the n as my f of t. And the Laplace transform of t to the n is sitting right there. And if I'm going to multiply t to the n by e to the at, and I want to do the Laplace transform of that result, then I just have to start with the Laplace transform of t to the n, but evaluate it at s minus a. So I'm going to copy that formula, but change the s to s minus a. So it's going to be n factorial divided by s minus a to the n plus 1. And notice that's the same thing that we got right here, but using a different approach. The end result. So another way to look at this one here is to think, okay, I'm going to start with the Laplace transform of t cubed, And since it's being multiplied by e to the negative 4t, I just have to do the Laplace transform for t cubed, but evaluate it at s minus negative 4, or evaluate it at s plus 4. And the Laplace transform for t cubed is 3 factorial over s to the 4. So in other words, 6 over s to the 4, and then evaluate that at s plus 4. And that's what gives you this 6 over s plus 4 to the 4. So it's just another way now that we could have done the Laplace transform of this. You could have done it using this idea, or in this case, you could have done it using this idea. All right, let's continue with our work. Create formulas for the Laplace transform of the first two derivatives of a function. And to do the Laplace transform of a derivative, we're going to refer back to the formula for Laplace transforms in general. So I want to do an integral from 0 to infinity of f prime of t dt times e to the negative st and then dt. Okay, this is the integral I want to calculate. Let's use the table method to do this. So I have to differentiate and integrate. And in the derivative column, I'm going to put the e to the negative st. So that's different than what we maybe did in other cases. But the reason I'm doing that is I want to put the f prime of t in the integrate column, because integrating f prime will take us right back to f. And differentiating e to the negative st will be negative s e to the negative st. And then we have plus minus. And now we do a horizontal product of those, and then, sorry, a diagonal product, and then a horizontal product of these entries, and that gets integrated. So looking at what was highlighted in the orange, we have e to the negative st times f of t, and then we're going to do minus, well, looking at the red product, we have a negative and a negative, so it's going to become plus, and then an integral of s e to the negative st times f of t dt. Now this was a definite integral, not an indefinite, so we actually need to put some limits of integration on some of these things here. And this first part that's considered done needs to be evaluated still from 0 to infinity, and this one needs to be integrated from 0 to infinity. Now notice that the s is a constant as far as dt is concerned, so this s here can be factored out. So we wind up getting, just factor that s out, and then an integral from 0 to infinity. And we put the f of t first, and then the e to the negative st next. Okay, now a couple things have to be true for us to, we have to assume a few things to proceed any further. The first thing we need to assume is that this function f of t is a function that for which e to the negative st will drag it to 0 as t goes to infinity. Now we know that this part here will shrink to 0, but this function, since we don't really know what it is, we have to make an assumption that it's a function that doesn't grow so fast that it will overpower the fact that this one is trying to shrink to 0 as t goes to infinity. And there's a little bit of theory here showing that the functions, that to make sure that we're working with a function for which this will be true. We're not going to get into this. All the functions that we're going to be working with in this class will be functions such that when you multiply that function by e to the negative st and then let t go to infinity, that this part will shrink to 0. So this will be a function that doesn't grow too quickly, so that when this part shrinks to 0, it'll drag this down to 0 with it. So with that assumption, when you evaluate it at 0, we're going to get 0 out of this. Sorry, when you evaluate at infinity, you're going to get 0 out of this. So 0 is the first result. And then minus, now plug in 0 for all the t's, and notice that we're going to get e to the 0, that's going to be a 1, and f of 0, well, we don't know what that is, so I'll just write f of 0. And then plus s times. Now I want you to notice something here about the integral that we have yet to compute, this integral sitting right here. This is the Laplace transform of f, by definition. So I can just put times capital F of s. And rearranging the terms a little bit, we get s times capital F of s minus f of 0. So that means the Laplace transform of a derivative of a function, as long as that function does not grow so quickly that this limit right here, oops, I didn't mean to move that, so that the limit as t goes to infinity of this product, we need that limit to be 0. So that's going to limit the kind of functions that we could be thinking about here. But as long as it's such a case where when you try to evaluate this product right here at infinity and you get 0, then the Laplace transform of the derivative of that function will be equal to s times the Laplace transform of just f, and then minus f of 0. That allows me to come up to the table here and put in s times capital F of s minus little f of 0. We'll use this formula in a moment, but first let's see if we can fill in the rest of this table. Going back down to the slide, to slide 5, and see if we can do the Laplace transform of the second derivative. Now I'm actually going to just borrow the formula from here because we can treat the second derivative, if you will, as the derivative of a first derivative. And so the Laplace transform of a second derivative, and we're just going to use this formula right here, where this is the Laplace transform of the first derivative. Right? Another way to have written this formula would have been like this. The Laplace transform of f prime is equal to s times the Laplace transform of just f minus f of 0. So this is another way to write this identity. And we're going to apply this, or we're going to essentially change the f's here, all the f's, to f primes. So this will be an f double prime sitting in these parentheses. So let me just actually copy this. Just drag it up here. Don't need to copy it, just bring it up here. And change all the f's in this statement to f primes. So it would look like this. The Laplace transform of f double prime is equal to s times the Laplace transform of f prime minus f prime of 0. Right? Just think of f as f prime. And then we can use the formula for the Laplace transform of f prime. So in other words, this right here can get substituted right in for this part. Okay, s times, and then let's just copy paste that. And then minus f prime of 0. And then when you remove the brackets and parentheses and such, it looks like the following. We get s squared times the Laplace of f, which is just capital F of s, minus s times f of 0, and then minus f prime of 0. Okay. Let's go back to our table and fill in this entry right here. The second derivative, the Laplace of the second derivative will be s squared times the Laplace of the original function f, minus, and now we have s times f of 0, and then minus f prime of 0. Now this starts to generalize. If I wanted to do f triple prime, which I didn't ask to do in this slide down here, but if you wanted to do f triple prime, we would effectively start with this statement and just change all the f's in this statement to f primes again. So this would become f triple prime, this would become a double prime, and this would become a double prime. And then you would do a bunch of nested formulas. So then right here, you would change this to this expression. Right? So the Laplace transform of a third derivative would be equal to s times, and then we can do the previous formula and plug it in. So let's copy that, paste it right here, and then minus, let me move all this over just slightly, minus this part right here I still have to write. So minus f double prime of 0. And then when you distribute the s across here, we have s cubed capital F of s minus s squared times f of 0 minus s times f prime of 0, and then minus 1 times f double prime of 0. And we get a result that we can put in here for the third derivative. You're going to see a pattern quickly emerge here. So third derivative means start with s cubed times f of s minus, and then the power of s drops to s squared, and f of 0 shows up. And then the power of s drops to s, and the derivative climbs to f prime of 0, and then the s disappears entirely, and we finish on f double prime of 0. So you can probably guess what a fourth derivative formula would look like. Just continue the pattern. And I meant to say over here that s had to be more than a, and I think that completes all of the entries of this table, of these tables. And of course you'd want to put these, say, in your notes on an exam that allows you to use notes so that you can refer to these formulas moving forward. Okay, so that wraps up everything that we were supposed to do on that slide. Let's do this next slide here. Find the Laplace transform of each side of the ODE with initial conditions below. Apply the formulas for the Laplace transform of derivatives, then solve for the Laplace transform of y. Okay, here we go. This is where, in a way, the rubber hits the road. And we're going to start with an ODE with initial conditions, and we are going to do a Laplace transform of it and see what happens. All right, let's begin by doing the Laplace transform of each side. So curly L of each side. Y prime plus 3y equals, and then a Laplace transform of the other side. Now, the property of linearity allows me to do the Laplace transform of y prime plus 3 times the Laplace transform of just y. So it becomes this statement, equals Laplace transform of t squared. Now, all these Laplace transforms that we can actually calculate or perform, let's go ahead and do. Let's start with the Laplace transform of y prime. That's going to be equal to, the entry in our table is s times the Laplace transform of y, which I'm going to go to capital Y of s. And then minus y of 0, little y of 0. Right, so all of that comes from this part of our statement using our table, plus 3 times the Laplace transform of y, which is, we're just going to use capital Y of s, equals, and now the Laplace transform of t squared. Well, t squared is t to the n, and the Laplace transform of t to the n is n factorial over t to the n plus 1. So we have to do 2 factorial, which is 2, right? 2 times 1, over t to the n plus 1, so over t cubed, and not t, but s, over s cubed. And now we are instructed to solve for y of s, and we also know that y of 0 equals negative 4, so this part right here we can replace with a negative 4. Let's do that first. So we have s times capital Y of s. If you want to be lazy, you can just write capital Y, minus negative 4, so plus 4, plus 3 times y of s, capital Y of s that is, equals 2 over s cubed. And we're supposed to solve for y of s, so we can gather its terms together, these two terms together, and factor out the y of s. So we have capital Y of s is times s plus 3. And this 4 over here I'm going to subtract to the other side, so we're going to have 2 over s cubed minus 4. And then the final step would be to divide both sides by this s plus 3. Or I'm going to multiply both sides by 1 over s plus 3. So we get y of s is equal to, and we have 2 over s cubed minus a 4, and then all of that is times a 1 over s plus 3. And I believe that's all we were expected to do for this problem. Get the y of s isolated after we apply the rule or the identity for doing the Laplace of a derivative. Took us to this stage, and then we had a Laplace of y over here as well. So we had 2 Laplaces of y's present, and we just had to isolate it. Now the next step to solving this ODE, which we won't do on this slide though, would be to, this is the Laplace transform of our solution. So we'd want to be able to reverse Laplace transforms, turn this back into a function of t, and that's going to be our solution to this ODE. But we haven't yet talked about how to reverse Laplace transforms. That'll be the topic 21, which is the third topic in this series of 4. So that's going to be next lesson, in other words. So we're just going to stop this slide here and move on and do one more example of how to do this, these initial steps in the first place. So now we have a second order ODE with initial conditions for y of 0 and y prime of 0. Again, we're going to begin by doing a Laplace transform of both sides. And I'm going to go ahead and apply the linearity property right now. So we have a Laplace transform of y double prime plus 4 times a Laplace transform of just y prime plus 3 times a Laplace transform of just y equals, and then we have to do a Laplace transform of t e to the 2t. Okay, so we Laplace transform both sides and use the linearity property, effectively distributing the Laplace transform. And now we're going to use a Laplace transform of y double prime formula. and that's going to give us s squared times the Laplace transform of just y, so times capital Y of s. I'm going to be lazy and just write capital Y. I won't put the of s. So s squared times y, and then we have minus s times little y of 0, and then minus y prime of 0. Okay, so these parts are the same. Let me color code them. And then we have plus 4 times, now we have to do the Laplace transform of y prime. Well, the Laplace transform of the first derivative was s times the Laplace transform of y, so s times capital Y, and then minus just y of 0. And for color coding purposes, let's make those green. Okay, so Laplace transform of y prime got applied. And now we have plus 3 times the Laplace transform of just y, so just capital Y, we'll say, equals, and now we have to do the Laplace transform of t times e to the 2t. Well, this is the case where we have an exponential times another function. Let's do that rule. Because if I can do the Laplace transform of just t, then I have to evaluate it at s minus 2. So the Laplace transform of t to the 1 is 1 factorial over s to the 1 plus 1. So it's 1 over s squared. But now I evaluated it at s minus 2. So we wind up getting 1 over, instead of s squared, we have s minus 2 squared. Right, that was me using, if you want to reflect on that a little bit more, maybe that was a bit too fast, I used the formula for the Laplace transform of t, but then I used this idea that if you take a function and you multiply it by e to the at, then you just got to do the Laplace transform of that function, little f, get capital F, but evaluate it at s minus a, where a is the coefficient of t here. So I used this property in conjunction with this formula to quickly get the Laplace transform of t times e to the 2t. Okay, now there's a few different expressions here. There's a bunch of y of zeros, and each y of 0 is a 2, so we want to, that y of 0 is going to be a 2, this y of 0 is going to be a 2. We also have some y primes of 0 need to be negative 1, so that's right there, that needs to be negative 1. And let me rewrite this now and remove parentheses and simplify some of these numbers. So we have s squared times y, capital Y that is, minus, this will be 2s, minus negative 1, so plus 1, plus 4s, capital Y, and then minus 8, right? We do distribute the 4 and the 2, so minus 8. Then plus 3, capital Y, and that's equal to 1 over s minus 2 squared. Now we want to gather all of the y terms together, so there's 3 of them, right? Those 3 right there. And I'm going to factor out the capital Y. So we have capital Y times s squared plus 4s plus 3. And all the terms that did not have y attached to those 3, I'm going to move over to the other side. So that's going to be we're going to add 2s to both sides and add 7 to both sides. So we get 1 over s minus 2 squared, and then I added 2s to this side, and I added 7 to this side. And then the final step, of course, is divide by this expression right here. Now be careful how you read this. This is not saying y of s squared plus 4s plus 3. This is not trying to say evaluate the capital Y function at this input. This is a y of s times this polynomial. So we really get y of s, right? Now I'm being unlazy and putting the of s back, is equal to, and then we're going to have all of this here. And then we're going to divide by this polynomial, or multiply by its reciprocal, in other words. So s squared plus 4s plus 3. And we'll call this one done. We have the capital Y of s function has been isolated. All right, and that's where we're going to pause our discussion on properties of Laplace transforms. In the next topic, we will talk about how to do inverse Laplace transforms. And then in the fourth topic of this series, we will put all the pieces together and solve ODEs from start to finish.